Go under. You don't need the ocean for this. 5 feet of a swimming pool will do. Close your eyes, let your ears fill, and have somebody stand at the edge and shout your name. You'll hear something. A flattened thud, a shape without edges, arriving from nowhere in particular. Now have them walk to the far end and shout again and try to point at them. You'll miss. Not by a little. When researchers put blindfolded volunteers underwater and played tones at 700 hertz, the subjects could barely separate sources unless they were pushed dozens of degrees apart. Underwater, a human being is a poor instrument. In pressure terms, our thresholds climb by roughly 40 to 60 decibels compared to what we manage in air, which is the difference between a conversation and a chainsaw. Measured in intensity, the penalty looks smaller, and honest acousticians will tell you the exact size of the gap depends on which unit you argue in, but the direction is never in dispute. We're worse down there, much worse. And the instinct almost everybody has about why is wrong. The instinct is that water muffles sound, that it's a thick, heavy, dampening medium, and the noise has to fight its way through. The opposite is true. Water is a spectacular conductor of sound. Sound moves through seawater at something like 4,900 feet per second, roughly 4.5 times faster than it moves through air, and it holds together over distances that would be unthinkable in the atmosphere. Low-frequency calls from fin whales have been picked up by hydrophone arrays hundreds of miles from the animal that made them. In the right layer of the deep ocean, where temperature and pressure conspire to bend sound rays back towards the middle instead of letting them escape, a sound can travel across an entire ocean basin. The sea is a loud place, and a startlingly clear one. As a medium for carrying sound, it beats anything else on this planet. The problem is you. Your ear was built to catch sound out of air and shove it into fluid. That's what the whole apparatus is for. The eardrum, the 3 little bones behind it, the funny shape of the outer ear, all of it exists to solve one engineering problem. Air is thin and inner ear fluid is thick, and getting energy from the one into the other without losing nearly all of it takes a mechanical transformer. Put your head underwater, and that transformer becomes pointless. There's fluid on both sides of it now. The eardrum has nothing to push against that isn't already being pushed, so you sit there in the pool, half deaf, and you assume everything else down there is having a slightly better version of your experience. A fish with tiny ears, a shrimp with a slightly worse version. Everybody straining to hear through the same soup. That's not what's happening. Most of the animals in the ocean aren't detecting the same thing you are. Forget the idea of a weaker signal or a muffled one. They're picking up an entirely different physical property of the same wave, one your ear has almost no access to, one that behaves according to different rules, falls off with distance at a different rate, and carries information yours throws away. And here's the part that turns a physics lesson into an argument with consequences. Nearly every instrument we lower into the sea to measure noise, every threshold written into environmental law, every impact assessment filed before a wind farm goes in or a seismic survey starts, measures the property you detect. The one most of them can't. That mismatch is decades old. It's still there. And it turns this whole subject into something a good deal bigger than aquarium trivia. Let's start where you have to start, which is with what a sound actually is when it's traveling through water. A sound wave is a disturbance passing through a material, and it has 2 faces. One event described 2 ways. The way a bank balance and a debt are 2 descriptions of one transaction. Picture a line of people packed shoulder to shoulder, stretching off into the distance. Somebody at one end gives a hard shove. What travels down the line? 2 things you could measure, depending on what you care about. You could measure the squeeze, how hard each person gets compressed against their neighbors as the pulse reaches them, or you could measure the shuffle, how far each individual person actually gets displaced forward and then back as the pulse passes through. The squeeze is pressure. The shuffle is particle motion. Every sound wave has both, always, in every medium. And which one dominates depends entirely on what the line is made of. If the people in that line are standing loosely, with room between them, a shove sends everybody staggering. Big shuffle, small squeeze. That's air. Air molecules are far apart and easily displaced, so a sound in air moves the air a lot and pressurizes it only slightly. Now pack the line so tightly that nobody can move at all. The shove still travels, but now almost nothing gets displaced, and instead everybody gets crushed. Small shuffle, enormous squeeze. That's water. Water is nearly incompressible. It resists being squeezed, which means the squeeze does the work, and the individual water particles barely move. There's a number that captures this. Acousticians call it acoustic impedance, and it's just the density of the material multiplied by the speed of sound in it. For seawater, the figure lands around 1.5 million in the standard units. For air, it's about 415. The ratio between them is roughly 3,600 to 1. Read that ratio again because it's doing a lot of work in this story. To produce the same amount of particle motion, the same physical back and forth shuffling of the medium, a sound in water has to carry about 3,600 times more pressure than the same sound in air. That's also why the decibel numbers you see quoted for underwater noise look so alarming. A pile driver described at 200 decibels underwater sounds like a number from a disaster film, and people share it as though it were comparable to standing next to a jet engine. It isn't comparable because the reference point is different. Underwater sound levels are quoted against 1 micropascal. Airborne levels are quoted against 20 micropascals. Different baseline, different scale, and then on top of that, the same energy produces wildly different pressures in the two media. You can't move a decibel figure from water to air by subtracting a fudge factor and calling it translated. People do it anyway, constantly. And it produces some of the most confidently wrong sentences on the internet. But set the units argument aside. The important consequence of that impedance number lands somewhere else entirely. It lands on the body of an animal. An animal in the sea is mostly water. Not approximately, not loosely. A fish is somewhere north of 70% water by mass, and the rest of it, the muscle and connective tissue and skin, has a density within a few percent of the seawater around it, which means its acoustic impedance is within a few percent as well. Sound doesn't notice it. When a sound wave meets a boundary between two materials of different impedance, some of it reflects. That's what an echo is. The bigger the mismatch, the more reflects. Air against water is a mismatch of 3,600 to 1, which is why a sound in the sea essentially can't escape into the sky, and a sound in the sky essentially can't get into the sea. They bounce off each other. But fish against water is a mismatch of nothing much. The wave arrives, passes clean through the animal, and continues on its way, barely aware that anything was in the path. You've seen this principle exploited, and you probably found it mildly unpleasant at the time. If you've ever had an ultrasound scan, the technician squirted a cold jelly onto your skin before pressing the probe down. That jelly is there for exactly one reason: to eliminate a film of air. Comfort has nothing to do with it, and neither does lubrication. Air between the probe and your skin would represent such a violent impedance mismatch that essentially all of the ultrasound would bounce straight back off it, and the image would be a white wall of noise. The gel matches the probe to your tissue so the sound can get in. Your body, acoustically speaking, is close enough to water to be worth entering. A fish is the gel. That's its whole acoustic identity. It's a water-shaped object made of water, sitting in water, transparent to the very thing it needs to detect. And this creates the problem that every animal in this story has to solve. So let's state it precisely, because everything from here follows from it. Detection requires relative motion. A sensory hair cell fires when it's bent. It bends when the structure it's attached to moves, and the fluid around it doesn't. Or the other way around. No difference, no bending, no signal. When a sound wave passes through an acoustically transparent animal, the entire animal oscillates together, in step, as one object. Every cell moves the same distance in the same direction at the same instant. Nothing inside it moves relative to anything else, which means nothing is detected. The animal is being moved by the sound and has no way of knowing it. In the same way you have no direct sensation of the earth rotating underneath you. Uniform motion is invisible from the inside. So if you want to hear underwater, you can't be uniform. You need to carry, somewhere in your body, a piece of material that refuses to move in step with the rest of you. And there are exactly two ways to build one. You can make it heavier. Something significantly denser than water has more inertia. So when the sound wave shoves the animal, the dense object lags behind. It gets left slightly in the wake of the body it lives in. That lag is relative motion, and relative motion can be measured by a hair cell. Or you can make it lighter, much lighter. A pocket of gas is 1,000 times less dense than the tissue around it and, crucially, wildly more compressible. When the pressure part of the wave arrives, the gas squeezes and rebounds while the surrounding flesh does essentially nothing. That's also relative motion, and it's a different kind, because it responds to the squeeze rather than the shuffle. Dense grain, or gas bubble. That's the entire menu. Every hearing system in the ocean, from an octopus to a blue whale, is some version of one of those two ideas, or an argument between them. And the two aren't equivalent. They detect different components of the wave. They behave differently with distance. They produce different information about where a sound came from. And the choice between them determines what an animal can and can't know about its world. Now we can start climbing. Before we do, there are 3 more properties of underwater sound that you have to have in your head, because without them, the rest of this is a parade of anatomy, and the argument evaporates. They're not difficult, they're just unfamiliar, because they don't matter much on land. The first one is about direction, and it's almost embarrassingly simple once somebody says it out loud. Pressure has no direction. It's what physicists call a scalar, which is a formal way of saying it's one number. At any given point in the water, at any given instant, the pressure is either higher or lower than normal by some amount. And that's the entire description. There's no arrow attached to it. If you were a pressure sensor and nothing else, you could tell me a sound had happened. You could tell me how loud and at what frequency. And you couldn't tell me anything at all about where it came from. Not roughly, not badly, nothing. Particle motion does have direction. It's a vector, an amount, and an arrow. The water at that point is moving back and forth along a specific axis, and the axis points at the source. A particle motion detector, in principle, gets the bearing for free. It comes bundled with the signal. That asymmetry sets up the central trade in this whole story. The pressure route gives you sensitivity and range and bandwidth, and hands you a signal with the address torn off. The motion route hands you the address, and then runs out of usable signal disappointingly fast. Almost every animal we're about to meet is somewhere on that trade, and the most sophisticated ones are the ones that found a way to run both at once and compare. The second property is about size, and it explains why fish couldn't just copy us even if evolution had wanted them to. You locate sounds in air using 2 tricks, both of which depend on your head being large. A sound coming from your left arrives at your left ear slightly before it reaches your right, by a few hundred millionths of a second, and your brainstem resolves that gap with absurd precision. And for higher frequencies, your skull casts an acoustic shadow, so the far ear hears a quieter version. time difference and level difference. That's the machinery. Both tricks die underwater, and they die for the same reason. Sound moves 4.5 times faster, so the time difference between your ears shrinks by that factor to something your brain has no calibration for. And your skull, being made of water-ish material sitting in water, casts almost no shadow at all. The sound goes through your head. You've been handed a pair of sensors that no longer disagree with each other in any useful way. Now shrink the listener. A herring is about 10 inches long. A sound at 100 hertz in seawater has a wavelength of roughly 50 feet. Against that wavelength, the animal is a rounding error. It sits inside a single crest entirely, with room to spare. There's no shadow, no delay, no gradient across its body worth reading. 2 ears on a herring, spaced an inch apart inside a 50-foot wave, receive functionally identical pressure signals. So a fish that wanted to know where a sound came from had to do something we never had to do. It had to read the arrow directly. The third property is the one that eventually breaks the law, and it's about distance. Out in open water, far from any source and far from any surface, sound settles into a simple, well-behaved pattern. Acousticians call it the far field, and in it the relationship between the two components of the wave becomes rigidly fixed. Divide the pressure by that impedance number and you get the particle velocity. Every time. The two are locked in step, in phase, in constant proportion. Which means, in the far field of a free field, you can measure one and calculate the other. And a cheap hydrophone tells you everything. Close to a source, that relationship falls apart. Right next to something that's vibrating, the water is still sloshing more than it's carrying a wave. The object pushes water out of the way, and that water has to go somewhere, so it flows around and comes back. A local circulation that has nothing to do with radiating sound and carries no energy away. This is the near field, and in it the particle motion is dramatically larger than the pressure would suggest, much larger. The two components come apart in both amplitude and timing. Where's the boundary? It scales with wavelength, roughly the wavelength divided by 6 and a bit. At 100 hertz in seawater, that puts the transition around 8 feet from the source. At 10 hertz, which is well within the range that many fish and invertebrates care about, it's closer to 80 feet. And around an object that oscillates back and forth instead of pulsing in and out. A swimming fish, a beating fin, a struggling prey animal. The near-field motion falls off with distance so steeply that doubling the range cuts it to an eighth. Hold those three properties together, and you can already see the shape of the argument. Pressure travels well and says nothing about direction. Particle motion says everything about direction and dies quickly near a source, then settles into a fixed ratio with pressure once you're far enough out. And the conversion between them, the arithmetic that lets you skip measuring the hard one, only works under conditions that require deep water, open space, and no reflections. The coastal ocean has none of those things. Most of the marine life that matters to us, and essentially all of the marine life affected by construction noise and shipping and seismic surveys, lives in water somewhere between 30 and 300 feet deep. That water is bounded on the bottom by a seabed that reflects and vibrates and transmits sound through the sediment itself, and bounded on top by the sea surface, which is the most extreme acoustic mirror on the planet. At the surface, water meets air across that 3,600 to 1 impedance jump, and the wave essentially can't cross. It reflects, and it reflects with its phase flipped, which means that right at the surface, the pressure cancels itself out and drops towards zero, while the particle motion does not. In a shallow bay, near the bottom, near the surface, near the source, inside a resonating layer of water, the tidy far-field relationship between pressure and motion is simply not in force. Measured comparisons have found the two diverging by more than an order of magnitude at the same point in the water. So the arithmetic that lets a hydrophone stand in for everything is an arithmetic that holds in the deep open sea and rarely holds anywhere a scallop bed or a herring nursery or a pile driver actually is. I'll leave that there for now. We'll come back to it at the end with teeth. What I want to do with the rest of this is climb. There's a ladder here, and it's a real one, not a tidy narrative invention. It runs from the crudest possible detector to the most elaborate, and at each rung, the biological problem changes. The change has nothing to do with the animal being bigger or the ear being prettier. Solving one level exposes a limitation you didn't previously have the luxury of noticing. 3 questions at every rung. What component of the wave does this thing detect? How far away can it work? And can it tell you where the sound came from? Rung 1 is about as simple as a sense organ can get. And it's older than fish, older than backbones, and old enough that it may have been doing an entirely different job when sound wandered into it by accident. It's a grain of rock in a bag of fluid. Take a small sack, fill it with fluid, line the inside with sensory hair cells, and drop in something heavy. That's a statocyst. It's one of the oldest sense organs on the animal tree. It shows up independently in jellyfish and worms and mollusks and crustaceans, and its original job had nothing to do with sound. Its job was down. An animal floating in open water has no automatic access to which way is up. Nothing in a neutrally buoyant body tells you your orientation, but a dense object in a fluid-filled chamber will always sink to the lowest point available to it. And if the walls of that chamber are wired with hair cells, then the identity of whichever hair cells are currently being pressed on tells the animal exactly how it's tilted. Roll the animal, and the stone rolls to a new patch of hairs. It's a plumb line made of meat. The classic demonstration of this is more than a century old, and still, I think, one of the most satisfying experiments in the history of sensory biology. Certain shrimp don't grow their own stone. They fill the statocyst with sand grains picked up from the seabed, and because they shed their exoskeleton as they grow, they have to empty the chamber and restock it with fresh grains after every molt. In the 1890s, the Austrian physiologist Alois Kreidel worked out what that meant. If the animal will simply load whatever small, dense particles are lying around, then you can control what goes in. He gave freshly molted shrimp a tank floored with iron filings. They dutifully packed their statocysts with iron. Then he brought a magnet near the tank. The shrimp reoriented. Pulled by the magnet instead of by gravity, the filings pressed against the wrong hair cells, and the animals swam tilted, correcting toward a false down that Kreidel was holding in his hand. A whole sense organ, hijacked with a stick of magnetized metal. It's a beautiful result because it doesn't just show that the statocyst detects gravity. It shows that the animal has no independent check on it. The organ reports the position of a stone, and the animal believes the stone. Now think about what happens to that arrangement when a sound wave comes through. The wave shoves the animal. The animal is acoustically transparent, so it goes along with the water, back and forth, the whole body oscillating in step, except for the stone. The stone is dense. In cephalopods, it's a crystal of calcium carbonate, several times heavier than the fluid around it, and heavy things resist changes in motion. So when the body lurches forward, the stone lags. When the body reverses, the stone is still going the old way. It rattles, microscopically, against the hair cells that were only ever meant to tell it which way was down. That's it. That's the whole mechanism. A gravity sensor held still by its own inertia while the body it lives in gets pushed around by sound. If you want a modern object that works on the identical principle, reach into your pocket. The accelerometer in your phone is a tiny mass suspended on microscopic springs. When the phone accelerates, the mass lags behind. The springs flex, and the flex is measured as a change in capacitance. That's how the screen knows to rotate. Same physics, same trick. roughly 500 million years apart. And this is where I'd push back on the word we've been using this whole time. What a cephalopod is doing when a sound arrives isn't much like what you do when a phone rings. It isn't detecting a tone in the air and parsing it. It's being nudged. Its body is being physically displaced rhythmically along an axis, and it can feel the displacement. That's closer to what your skin does when a truck goes past than to what your ear does when somebody speaks. It's touch. Touch performed at a distance by a medium dense enough to carry the shove. The measurements back that up with unusual clarity, and they come from a line of work that started in Norway. In 1990, Andrew Packard, Hans-Erik Karlsson, and Olav Sand ran an experiment on 3 cephalopods: the common octopus, the common cuttlefish, and the European squid, inside a standing wave tube, a rig that lets you control the pressure and the particle motion separately instead of leaving them locked together the way they're in open water. That separation is the crux of the whole design. In a normal tank, you can't tell which component an animal is responding to because both arrive at once. In the tube, you can. They conditioned the animals, a low-frequency vibration paired with a weak stimulus, until the animal learned to expect one from the other and gave itself away with a change in breathing or a jet. Then they walked the frequency down and the amplitude down and found the floor. The animals responded from about 1 Hz to about 100 Hz. Best sensitivity sat at the very bottom of that range, below about 20 Hz. That's a rate of oscillation so slow that in air you'd feel it in your chest more than you'd hear it. Thresholds, expressed as particle acceleration, went below 4/1,000ths of a meter per second squared, which is to say roughly 4/10,000ths of the acceleration you feel standing still on the surface of the Earth. That's a delicate instrument. And the parameter they were responding to was particle acceleration. In a tube where you can pull the two apart, the cephalopods tracked the motion and ignored the squeeze. 20 years later, Aaron Mooney and colleagues at Woods Hole came at the same question from the other end, recording the electrical response of the squid's auditory system directly rather than waiting for a behavior. Long-fin squid gave responses from around 30 Hz up to about 500, best somewhere between 1 and 200. Same conclusion, different instrument, and the title of the paper says the quiet part plainly: sensitivity to low-frequency particle motion and not to pressure. More recent work on cuttlefish behavior in the infrasonic range points the same way. So, rung 1. What does it detect? Particle motion, specifically acceleration, at very low frequencies. Can it tell you where? Partly. The organ is inherently directional because the stone lags along whatever axis the shove is happening on, and different patches of hair cells are oriented differently. What it gives you is an axis. What it can't give you, on its own, is which end of that axis the sound came from. A squid feeling a 15 Hz oscillation knows the line and has a coin flip about the direction along it. We'll see that same ambiguity again in fish, and we'll see the elaborate machinery vertebrates built to resolve it. How far does it work? This is where the level starts to hurt. Particle motion in the far field falls off in proportion to distance, same as pressure. Near a source, it's much stronger. But an animal with a staticist and nothing else is stuck with a fairly high threshold and a very narrow band. Roll all that together, and the practical envelope is small. A cephalopod monitors the space around its own body, plus whatever unusually violent low-frequency events happen further out. The neighborhood is past its reach, and it has a harder ceiling than that, which comes from what it doesn't have. A squid has no gas in its body. No bubble, no bladder, no cavity of any kind that can be squeezed by the pressure component. Its tissues are water, its stone is rock, and neither compresses. So the entire pressure half of every sound wave that passes through a squid does precisely nothing to it. The animal is deaf to it in the strictest possible sense. Its equipment has no way to take delivery. Half the wave isn't addressed to it. There's one genuine complication worth flagging because I'd rather flag it than let you find it later and think I was hiding it. Cuttlefish do have gas in them. The cuttlebone, that chalky oval you've seen clipped inside a bird cage, is a rigid chambered structure the animal floods and drains to control its buoyancy, and it holds gas at all times. In principle, a gas space near a sensory organ is exactly the kind of thing that could act as a pressure transducer. In practice, nobody has demonstrated that the cuttlebone contributes to hearing, and the behavioral evidence still points at particle motion. So it stays an open question, and if it ever gets answered in the affirmative, the cuttlefish becomes a much more interesting animal than this section is giving it credit for. Where does that leave the level? You have a detector that tells you the world is moving and roughly along what line. It's exquisitely sensitive at the very bottom of the frequency range and blind above a few hundred hertz. It has no access to pressure, which means no access to the component that travels well. And it's a single-point sensor, one reading, one axis, one number at a time, which is fine, right up until you need to know something about a moving object rather than about a passing wave. Where is it? How big is it? Which way is it going? Is it accelerating toward me? A single accelerometer can't answer any of those. To answer them, you need many detectors, spread across a surface comparing notes. That's the next rung, and it belongs to fish. You've seen the organ 100 times without registering it. That faint seam running down the flank of a bass, or a trout, from behind the gill cover to the base of the tail. Sometimes visible as a dotted line, sometimes as a slightly different shade of scale. People assume it's a marking, it's a sense organ, and it's the reason a fish in a bucket knows your hand is coming before it touches. Underneath that seam is a canal, buried just below the skin, open to the water through a series of small pores. Inside the canal, spaced along its length, are the receptors, clusters called neuromasts. And a neuromast is, in its essentials, the same device we just took apart, rebuilt for a different job. Same hair cells, same principle of bending. What's changed is, what does the bending? Instead of a dense stone lagging behind, each neuromast has a blob of jelly called a cupula, and the hair cell cilia are embedded up inside it. The cupula sticks out into the water. When water flows past, the jelly gets dragged. The hairs inside it bend, and the cell fires. It's a flag in a breeze with nerve endings in the pole. Fish carry these in two configurations, and the difference between them isn't cosmetic. Some sit right out on the skin, exposed, and those respond to the speed of water flowing over the body. Others sit down inside the canals, sheltered, reachable only through the pores. A canal neuromast doesn't feel the outside flow directly. It feels the difference in pressure between the pore in front of it and the pore behind it, which drives a little slosh of fluid inside the canal. Because it reads a difference across a span instead of an absolute value, it ends up responding to how fast the flow changes instead of to the flow itself. Two filters, two jobs. The exposed ones give you a steady read on the current you're sitting in. The buried ones ignore steady current and light up when something changes. Now the important part, and the reason this organ isn't simply a second ear. Everything we said about acoustic transparency still applies. When a distant sound washes through a fish, the fish and the water move together. There's no flow across the skin because the skin is going the same place the water is. A neuromast in that situation feels nothing. Zero. A fish's lateral line is completely indifferent to a sound from far away, no matter how loud, as long as the animal and the medium are moving in step. What the lateral line needs is a gradient. It needs the water at the fish's nose to be doing something different from the water at its tail. And gradients like that exist in exactly one place, close to whatever's causing the disturbance. Remember the near field. Right around a source, The water sloshes around the object, circulating, going one direction on one side and the other direction on the other. That's a flow field with structure in it. And structure is what a distributed array of sensors is built to read. 20 or 30 neuromasts down each side of a body, each reporting the local flow at its own position. And the fish's brain has something a single accelerometer could never produce: a picture. The Dutch physiologist Sven Dijkgraaf, who spent decades on this system and whose 1963 review still anchors the field, gave it a name that has never been improved on: distant touch. That's precisely what it is. Touch, extended a body length or two out into the surrounding water by the fact that water is dense enough to transmit a push. A fish swimming past a rock feels the rock, because its own bow wave bounces off the rock and comes back distorted. It's groping the environment with a field of water it carries around itself. If you want to see the system taken to its limit, look at a fish that has nothing else. In the caves of northeastern Mexico, there's a population of the Mexican tetra that has lived underground long enough to lose its eyes entirely. The eyes start forming in the embryo and then degenerate. Adults have skin over the sockets. These animals navigate complex three-dimensional cave systems, find food, avoid walls, and hold position in flow, in absolute darkness. And they do it substantially with an expanded lateral line. They carry more superficial neuromasts than their river-dwelling relatives, concentrated on the head. And they've been observed to increase their swimming speed when entering unfamiliar space, which reads as a deliberate strategy. Swim harder, generate a stronger flow field around yourself, get a better return off the walls. An animal turning up its own illumination, except the illumination is water. Engineers have taken the hint. There's a line of work going back about 20 years on artificial lateral lines, arrays of tiny flow sensors mounted on underwater vehicles, meant to give a submersible the same close-range hydrodynamic picture. In murky water where cameras fail, and where active sonar would announce your presence, it works. The fish still does it better, and it works. So what does this rung buy you? Spatial resolution, for one. The staticist gave you a single vector. The lateral line gives you a map. This part of my body is being pushed this way, that part that way. And from the pattern I can reconstruct where the disturbance is and roughly how big it is. It resolves the ambiguity that a single sensor couldn't. It supports behaviors that would otherwise be impossible. A school of several thousand fish holds formation and turns as a unit, each individual maintaining spacing by feeling the flow off its neighbors. Blinded fish, still school. Fish with the lateral line disabled don't hold position properly. It supports the escape response too, in partnership with the ear. A predator lunging at a fish generates a sharp acceleration in the water ahead of it. And that signal, funneled through some of the largest nerve fibers in the vertebrate body, triggers the sea start. The animal folds into a C and fires off in the opposite direction in a few thousandths of a second, faster than the decision could travel through a conventional circuit. That whole reflex is built on detecting a flow gradient. And it buys all of that inside a very short leash, around an object that's oscillating back and forth, which describes almost anything alive. The near-field water motion falls off with the cube of distance. Cube. Move twice as far away and the signal drops to an eighth. 3 times as far, and it's a 27th. This isn't a curve you can push against with better sensitivity. Adding 10 decibels of sensitivity to a system with that fall-off buys you a few inches, which is why every measurement of lateral line performance converges on the same unglamorous number. 1 body length, maybe 2, for a big signal in still water. That's the working range of the most sophisticated flow sensing array in the animal kingdom. There are 2 further limitations worth being honest about. The first is self-noise. A swimming fish generates enormous flow across its own skin, far larger than anything it's trying to detect, and it has to suppress that. Nerve fibers run from the brain out to the hair cells and turn them down during the animal's own fast movements, so it doesn't deafen itself every time it flicks its tail. The second is that the lateral line is close to useless in turbulence. Put a fish in a fast churning current and the environment is screaming across every neuromast it owns. A river fish in flood is, for practical purposes, operating without the sense. I find it a little poignant that the most elegant solution on this ladder is also the shortest ranged. Evolution built a system that can reconstruct the shape of a rock from the water bouncing off it. And it works out to about the length of the animal, and then the physics simply closes the door, which leaves the problem unsolved. Everything important to a fish happens further away than one body length. The predator that's going to eat it, the reef it needs to settle on, the shoal it needs to join, the surf line marking the coast. All of that sits out in the far field, where the water moves as one piece and the lateral line has nothing to grip. To reach out there, you have to go back to the inertia trick. You have to go back to a dense object lagging behind a body, and you have to make it enormously better than a squid's. Open a fish's skull, and you won't find an ear canal or an eardrum or anything that looks like a route from the outside world to the inside of the head. There's no hole. The whole apparatus is sealed in bone on either side of the brain case, with no connection to the water whatsoever, which is exactly what you'd expect from an animal that doesn't need one. The sound is already inside. It walked in through the skull. What's in there's a chamber system that any vertebrate would recognize, because it's the same inner ear you have, minus one late invention. 3 semicircular canals arranged at right angles, filled with fluid, reporting on rotation. Turn your head, the fluid lags, and you know you turned. Below them, 3 fluid-filled sacs, each with a patch of hair cells on the floor and a stone sitting on the patch. The 3 sacs have names worth learning because they'll come back. The utricle, the saccule, and the lagina. You have the first 2. Your utricle and saccule sit under your semicircular canals doing balance and gravity, exactly as they do in a fish, with a crust of tiny calcium crystals resting on the sensory patch instead of a single stone. Your lagina, in your deep ancestry, elongated and coiled and became the cochlea. Fish never took that road. They kept the sac. The stones in a fish are called otoliths, and a crust of grit is the wrong picture entirely. They're single, solid, individually shaped mineral bodies, and in a large fish, they can be the size of a fingernail. Each of the 3 sacs has its own. The sagitta in the saccule, usually the biggest and usually the primary hearing organ. The lapillus in the utricle, the asteriscus in the lagina. In a cod or a drum, you can pull them out with tweezers and hold them in your palm, and they look like polished white pebbles with sculpted edges, unmistakably manufactured rather than scavenged. They're made of aragonite, a crystal form of calcium carbonate, the same mineral a pearl is built from. And the number that matters, the number this entire rung is built on, is the density. Measurements on the sagittae of the large yellow croaker put the density around 2,780 kilograms per cubic meter, which is roughly 2 3/4 times the density of seawater. Its acoustic impedance comes out around 9 to 11 times, that of the water outside. 9 to 11 times. Set that against the fish's own tissue, which, as we established, is within a few percent of the water. In a body that's acoustically almost invisible, that stone is a rock in a fog bank. Sound passes through the animal as though it weren't there, and then hits something that won't cooperate. The mechanics follow with no further cleverness required. The sound wave shoves the whole fish. The fish moves. The otolith, being 2 3/4 times heavier per unit volume, has more inertia and lags. The sensory patch beneath it, being part of the fish, has already moved. So the hair bundles get sheared, dragged sideways under a stone that's still catching up. Estimates of how small that shear can be and still be detected are, frankly, difficult to believe. Hair cells across vertebrates respond to bundle deflections on the order of a nanometer, and some measurements put the threshold well below that. A nanometer is a few atoms across. The organ is registering a relative displacement between two parts of a fish's head smaller than the width of a molecule, thousands of times a second, and reporting it up a nerve. I don't think that number lands the first time you hear it, so here's a comparison that might. If you scaled a hair bundle up to the height of the Empire State Building, threshold deflection at the top would be around the width of your thumb. Now, is any of that actually established, or is it a plausible story told over an anatomy diagram? It's a fair question. A dense stone over a sensory patch is suggestive, but suggestive isn't evidence. And the honest test is whether changing the stone changes the hearing. It does. And the natural experiment that shows it came out of fish farming, which isn't where anybody was looking. Aragonite isn't the only form calcium carbonate can take. It can also crystallize as vaterite, which is less dense, less orderly, and grows into a lumpier, larger, glassier structure. In wild fish, vaterite otoliths are rare, a small percentage, usually one stone on one side. In hatchery-raised Atlantic salmon, they're not rare at all. A study published in 2016 surveyed farmed salmon across several countries and found vaterite otoliths at rates that in some populations exceeded half the fish examined, orders of magnitude above the wild baseline. Nobody is entirely sure why. Growth rate, genetics, temperature, and rearing conditions have all been implicated, and it's still argued about. The relevant part is what it does. The researchers modeled and measured the acoustic consequence, and a vaterite otolith degrades hearing substantially. With the loss concentrated in the frequency range these fish actually use. Change the density and structure of the stone, and the animal hears worse, in a way that follows directly from the physics. That's the mechanism confirming itself from an unexpected direction. It's also, incidentally, a real welfare and conservation question, because a hatchery salmon released to supplement a wild run may be going out into the river partially deaf. And nobody counted that when they counted the smolts. While we're here, there's a second thing about otoliths that has nothing to do with hearing and is too good to leave out, partly because it explains why fisheries labs have millions of them in drawers. Otoliths grow by accretion, laying down a new layer of crystal on the outside, and the composition of the layer shifts on a daily cycle. Slice one, polish it, put it under a microscope, and you get rings. Daily rings, and coarser annual bands like a tree. You can read the exact age of a fish off its ear stone. Better than that. Because the crystal incorporates trace elements from the surrounding water as it grows, the chemistry of each ring records the water the animal was swimming in at that moment. Strontium ratios distinguish fresh water from salt, which means you can take a single dead salmon, section the stone out of its head, and reconstruct where that individual fish was, month by month, for its entire life. The hearing organ is also a flight recorder. Nobody planned that. It's what happened anyway. Back to the argument. We now have a detector that's a serious upgrade on the squids. Bigger stone, denser stone, thousands of hair cells instead of a modest patch, 3 separate sacs instead of one chamber, and a dedicated 8th cranial nerve running the traffic. But the physics hasn't changed. This is still inertial detection of particle motion. It's still, at bottom, an accelerometer, which means the range problem hasn't gone anywhere. Better sensitivity extends the envelope, and it extends it usefully. A cod detecting particle motion works over tens of feet instead of inches, but you're still reading the component of the wave that has no compressible structure behind it, in a body that has no compressible structure in it, and there's a ceiling on that. In fish with no gas anywhere near the ear, hearing tops out somewhere in the low hundreds of hertz and thresholds stay high. What the upgrade does buy, and buy spectacularly, is direction. And the way it does, it's the most elegant piece of engineering in this entire story. No new organ was involved. That's the first thing to get straight. Fish never bolted a compass onto the side of the ear. The direction sense is built into the individual sensory cell, the same hair cell we've been leaning on since the state assist. And to see the trick, you finally have to look at one properly, because we've spent this whole climb treating it as a black box that bends and fires, and the box is about to become the story. A hair cell has no hair. What it carries on its top surface is a bundle of stiff rods called stereocilia, packed together like a fistful of drinking straws, cut to different lengths and arranged in a staircase. Shortest rows at one edge of the bundle, tallest at the other. In a fish, the top of the staircase is crowned by one true whip-like cilium standing above the rest, and running between the rods, from the tip of each one up to the flank of its taller neighbor, are filaments so fine that nobody pinned them down until electron microscopy got good enough in the 1980s. They're called tip links, and they're the exact place where motion becomes nerve signal, the point, in every hearing animal on this planet, where physics stops and biology starts. The conversion is brutally direct. The tip links are attached to gates, ion channels, in the membrane of each rod. Tilt the bundle toward its tall edge, and the geometry stretches the links. The links pull the gates open, charged atoms flood in, the cell's voltage jumps, and transmitter is dumped onto the nerve. Tilt the bundle back the other way, and the links go slack, the gates flop shut, and the cell falls silent. Notice what's missing from that chain. There's no chemistry doing the sensing. When your eye catches a photon, the photon triggers a molecule, which triggers a cascade of other molecules, which eventually closes a channel. It's a magnificent amplifier, and a slow one, which is why fast events smear together in your vision. The hair cell skips all of it. The stimulus itself hauls the gate open, mechanically, like a hand on a rope. The gates respond within microseconds. That directness is the only reason hearing can follow hundreds or thousands of cycles per second while your eyes lose track of a flickering bulb. Now run the experiment that matters. Push the bundle toward its tall edge. The cell fires hard. Push it exactly the opposite way. The links slacken past their resting tension. The gates shut, and the cell goes quieter than silence. It drops below its own resting chatter. Push it sideways, at right angles to the staircase, almost nothing. The response follows the axis of the staircase, full strength along it, fading to zero as you rotate away from it, which means a hair cell does something no microphone does. A microphone reports that sound happened. A hair cell reports motion along one particular line in space, with a loud end and a quiet end. It's an arrow, and once your detector is an arrow, direction stops being a calculation you perform on a signal and becomes a matter of which cells are talking. Look down at the sensory patch under an otolith. Researchers have done exactly that, patch after patch, species after species, under scanning electron microscopes. It's a body of work associated with the American biologist Arthur Popper more than anyone, who spent decades cataloging the ears of everything from goldfish to deep-sea fishes. And the arrows aren't all pointing the same way. The patch is divided into territories. In one region, thousands of hair cells stand with their staircases aimed toward the head. In the neighboring region, toward the tail. Other groups aim up or down, and the borders between territories are sharp, like painted lanes in a parking lot. The layouts vary between species. A handful of standard patterns keep turning up, and nobody entirely knows why one lineage prefers one map over another. Within a species, though, the map is stereotyped, as consistent as the wiring diagram of an appliance. Now stack the geometry. Each of the three otolith sacs sits at its own angle in the skull, the utricle roughly horizontal, the saccule roughly vertical, the legena filling in a third plane. 3 stones, 3 tilted sensor beds, each bed subdivided into opposing platoons of arrows. A sound arrives. The particle motion runs along one specific axis in three-dimensional space. The stone in each sack lags along whatever component of that axis its sack can see, shearing some platoons of hair cells hard, driving their opposite-facing neighbors into silence, leaving the perpendicular ones untouched. The pattern of who fires and who goes quiet across 3 organs and tens of thousands of cells encodes the axis of the motion redundantly with information to spare. The fish's brainstem then does what your phone does with its 3 accelerometers mounted at right angles, reads the components, reconstructs the vector. That's the elegant engineering. A field of oriented single-axis detectors, doing vector arithmetic in bulk. No dish, no funnel, no external ear anywhere in it. The fish doesn't work out where a sound is by comparing 2 ears the way you do. Every patch of its ear is already a direction measurement. It hears in vectors natively, the way you see in color. 2 details make it better. Fish never stop adding hair cells. A young fish has thousands. An old one can have hundreds of thousands, the ear thickening its own resolution across a lifetime. And when hair cells die, fish grow them back. Yours do not. When the arrows in your cochlea fall over, they stay down, which is what most human hearing loss is. A fish resurfaces its ear the way a road crew resurfaces a highway, without ever closing the road. So the picture at this rung looks nearly complete. Sensitivity to displacements below a nanometer. Tuning to the component of the wave that carries direction. A 3-axis array that extracts that direction natively, in hardware. And it still has the coin flip. Go back to the arrow. A hair cell fires hardest along its axis, but sound is an oscillation. Back and forth both ways along the line, every single cycle. The stone shears the bundle one way, then the other way, hundreds of times a second. Averaged over even a few cycles, the axis is unmistakable. And the sense, meaning which end of the axis the sound actually lives at, is simply not in the data. The fish gets the line and not the arrowhead. Most of the compass eliminated, and the last lethal ambiguity intact. This way, or exactly the opposite way. The squid had this problem. We forgave the squid because the squid is a point sensor with a narrow band and a short reach. But here the problem is again. 2 rungs up the ladder, having survived every upgrade. Bigger stones, denser stones, oriented arrays, vector readouts, and none of it laid a finger on the problem because it was never a hardware limitation. It's baked into the quantity being measured. Motion along a line is symmetric. No motion detector at any level of refinement can break that symmetry on its own. Think about what the coin flip costs in the open sea. A predator closes from the left. The fish reads the axis perfectly, left-right. Now it has to flee along the line, one end or the other. Half the time, straight down the throat. A sense that delivers a flawless bearing with a 50% chance of pointing at the wrong end of its adair. Breaking the tie requires a second, different measurement. Information the motion channel can't supply at any sensitivity. The missing bit lives in the other half of the wave, the squeeze. The component that, as we established hours ago, passes through a watery body doing precisely nothing. To read it, a fish needs the one thing its transparent body doesn't have, something compressible. It needs a bubble. And here the story does something better than invention. It does repurposing, on a scale that ought to be illegal. Most fish were already carrying one. It runs along the top of the body cavity, tucked under the spine, a silvery gas-filled bag that takes up around 5% of the body's volume in a marine fish, a little more in fresh water, the swim bladder. And its day job has nothing to do with sound. Its day job is floating. Muscle and bone are denser than seawater, which means a fish, left to its own devices, is a sinking object. It can fight the sink by swimming, but that's a tax paid every second of its life, and the ocean doesn't tolerate animals that waste energy. The bladder cancels the tax. Inflate a bag of gas to just the right volume, and the whole animal averages out to the density of the water around it. Weightless. A fish hanging motionless in mid-water is in orbit. The history of the organ is stranger than the function. The best evidence says the bladder began its career as a lung. Early bony fish, living in warm, shallow, oxygen-starved water, gulped air at the surface and held it in a pouch off the gut. And that pouch split the future of the vertebrates in two. In one lineage, it stayed a lung, and you're running two of them right now. In the other lineage, better gills made air breathing optional, and the pouch sealed itself, migrated to the top of the body cavity, and became a flotation tank. Hold that thought properly. The organ that's about to solve underwater hearing is a repurposed lung. You and a goldfish inherited the same ancestral air sac. You talk with yours. The goldfish listens with its, because put that bag in the path of a sound wave and everything changes. Every other part of the fish, we established, ignores the pressure half of the wave. Flesh is water. Water doesn't compress. The squeeze passes through and finds nothing to squeeze. Gas is different. Gas is on the order of 10,000 times more compressible than water. When the compression crest of a sound wave arrives, the bladder is squashed smaller. When the rarefaction trough arrives, it springs back larger. The bag breathes with the wave, in and out, at the frequency of the sound, however many 100 times a second that is. And a pulsing bubble in water does something very specific. It becomes a source. Its wall is pushing water back and forth, which means it's radiating particle motion into the tissue around it, the sloshing, near-field kind, strongest close by. The fish's ears, with their stones and their fields of arrows, are sitting a short distance away, inside that slosh. Raid the chain slowly, because it's the hinge of the whole story. Pressure arrives, and on its own it's undetectable. Pressure squeezes gas. Gas converts the squeeze into wall motion. Wall motion is particle motion, and particle motion is detectable. The swim bladder is a transducer. It takes the half of the wave the fish's body can't feel and rebroadcasts it privately, inside the fish, in the one currency the ear accepts. Think about what that buys. Pressure is the component that travels. It holds up over distance. It carries the high frequencies. It's the long-range channel of the ocean. An ear locked to particle motion alone is stuck with whatever motion survives the trip, which at any respectable distance isn't much. An ear with a bladder behind, it's reading the traveling component, the one that crossed the bay, the one that came down from the surface, the one that left the source a mile away. Sensitivity jumps. Bandwidth stretches upward, because a bubble will happily flutter at frequencies far above anything that could shove a whole fish back and forth. The animal stops hearing the space around its body and starts hearing the neighborhood. You would be right to want evidence, and the cleanest evidence comes from comparing fish that have the organ with fish that lost it, and from the strange, careful place that comparison had to be done. Flatfish spend their adult lives pressed against the seabed. A place or a dab has no use for neutral buoyancy, since floating is the last thing it wants, and as it matures, the swim bladder is simply deleted, gone. Same basic inner ear as a cod, same stones, same hair cells, no bubble. In the 1970s, Anthony Hawkins and his colleagues from the Marine Laboratory in Aberdeen measured what those animals could actually hear, and they refused to do it in a tank. That refusal matters more than it sounds. A concrete tank in a basement is an acoustic hall of mirrors, reflections everywhere, pressure and particle motion scrambled out of their open water relationship, so a tank audiogram can end up measuring the wrong quantity without anyone noticing. So they ran the experiments in the open water of Scottish sea locks, cages, calibrated sources, patient conditioning of wild-caught fish, in conditions where the physics was honest. The result draws the line as cleanly as biology ever does. Cod with a healthy bladder, sensitive broadband, responding well up through the hundreds of hertz, reading the pressure wave. Dab in place, no bladder. A narrow window down at the bottom of the spectrum, responding to particle motion and nothing else. Deaf to the traveling component of the very same sounds. Same seawater, same ancestral ear. One organ different, and the whole acoustic world either opens or stays shut. The surgical version of the experiment says the same thing. Gently deflate the bladder of a fish that has one, and its hearing at the higher frequencies sags. Let the gas back, and the hearing comes back. The bubble is the antenna. Antennas, though, come with bills attached, and this one comes with 3. The first is tuning. A bubble has a natural ring, a resonance, set by its size, and the pressure sitting on it. And that pressure changes every time the fish changes depth. Dive, and the gas compresses, the bag shrinks, the resonance shifts, the buoyancy fails. Rise, and it all runs the other way. A sealed bladder has to be actively managed, and the machinery that manages it's worth a sentence of respect on its own. A gland backed by a dense mesh of countercurrent capillaries called the rete mirabile, the wonderful net, which can pump gas out of the blood and into the bag against hundreds of atmospheres of pressure. A fish at depth is inflating a balloon against a force that would crush industrial equipment using nothing but plumbing. The second bill is exposure. The same impedance cliff that makes the bladder a good transducer makes it a beacon. Sound crossing a fish ignores the flesh, as we established, and then slams into the gas and reflects hard. Point an echo sounder at the sea, and what you mostly see when you see fish is bladders. The great majority of the echo off a fish comes from that one organ, a fact the fishing industry has built itself around. The schools scrolling across a trawler's sonar screen are constellations of glowing bubbles with animals discreetly attached. The organ that lets a herring hear the ocean is the organ that lets a factory ship find the herring from half a mile above. And bladders don't only betray fish to trawlers, they shine brilliantly at another kind of searchlight. One we'll meet later in this story, mounted in the forehead of a predator that hunts with sound. File that away. The third bill is the one that drives the next rung, and it's pure geometry. The bladder sits in the middle of the body. The ears sit in the skull. The re-radiated slosh coming off the bladder wall is near-field motion, and near-field motion, as the lateral line taught us, dies fast. Most of the converted signal is spent just crossing the fish. In a small fish, the ears are close enough to catch a useful fraction. Grow larger, and the gap widens, while the physics stays merciless. Evolution answered the geometry problem the way a rigger would. Close the distance. Several unrelated lineages grew forward extensions of the bladder, horns of gas reaching up toward the back of the skull. In some species pressing directly against the ear capsule, shaving the gap to nearly nothing. That works. It's the obvious move. One lineage did something else. Something with moving parts. In 1820, in Leipzig, a German anatomist named Ernst Heinrich Weber was dissecting carp, and at the front of the body cavity, where the swim bladder narrows toward the spine, he found something that shouldn't have been there. A chain of small bones, 4 of them on each side, paired left and right, running from the front wall of the bladder up to a fluid space at the back of the skull. Delicate, articulated, obviously mechanical, a linkage, in a place where the anatomy books said there was nothing but vertebrae. Weber looked at that chain and made a leap that was, for his century, almost reckless. He knew the human middle ear, 3 tiny bones, carrying vibration from the eardrum to the inner ear. Here were small bones bridging a gas bag and an ear. He proposed they did the same job, that the chain was an ear mechanism and the bladder was working as an eardrum buried in the middle of the fish. He was so convinced that he described the little bones with the vocabulary of hearing. The scientific world filed the idea away as anatomy's business, unprovable either way, and there it sat for 100 years. He was right. And the way we know he was right is one of the most charming episodes in the history of biology. In the 1920s, the Austrian physiologist Karl von Frisch, the same man who would later crack the honeybee's waggle dance and collect a Nobel Prize for it, was irritated by a confident consensus of the day that fish were deaf. Textbooks said it plainly: no cochlea, no eardrum, no ears worth the name, therefore no hearing. Von Frisch kept a European catfish blind, and he did the simplest experiment available to a man with a fish and a whistle. Before every feeding, he whistled. Within days, the catfish came swimming out of its hiding place at the whistle alone, before any food touched the water. A blind fish, responding to a sound, in a controlled and repeatable way. Fish heard. The consensus was dead, killed by a pet. Von Frisch and his students then went further, and this is where Weber's century-old guess came due. They tested fish with the bone chain against fish without it, and the difference wasn't subtle. The chain bearers heard better by orders of magnitude, and heard higher, into frequency ranges no other fish could touch. And when the experimenters surgically interrupted the chain, or emptied the bladder it was connected to, the high-frequency hearing collapsed, while the low-frequency hearing survived. The linkage was doing exactly what Weber said it was doing, carrying the bladders trembling to the ear, bone by bone. Here's the machine in motion. A sound wave sweeps through the fish. The bladder's front wall flutters, squeezed and released at the frequency of the sound. The first bone in the chain, the tripus, is anchored to that wall, and it rocks with every flutter. The rocking passes along the chain, tripus to intercalarium to scaphium to claustrum, each a small lever pivoting on the spine, and the last bone pushes on a little fluid-filled sinus at the base of the skull, which is plumbed directly into the fluid of the inner ears, both of them. Compression waves in the bag become rocking bones, become pulses in the ear fluid, become shear under the stones, become nerve fire. It's a middle ear, a real one, in function and in principle, built where no textbook expected it, in the middle of a fish's back. And the parts list is the best joke in the whole apparatus. Your middle ear bones are salvage. 2 of them began deep in ancestral time as pieces of reptilian jaw joint that shrank, detached, and were re-employed for hearing. The carp's middle ear bones are also salvage, from a different scrapyard. They're modified vertebrae, pieces of the first few segments of the backbone that broke away from their old jobs, reshaped into levers, and went into the sound business. 2 lineages, 2 junk drawers, 1 solution. Nobody designed either ear. Both were assembled from whatever was lying around next to the problem. The fish that carry Weber's chain are called otophycens, and once you know the name, you realize you've known the fish all your life. Carp, goldfish, minnows, the tetras in a million aquariums, piranhas, loaches, and every catfish on Earth. Somewhere around 10,000 species, which is roughly 2 out of every 3 fish species in fresh water. Let that ratio register. This is no curiosity tucked away in one odd family. In the rivers and lakes of this planet, the fish with the bone chain middle ear are the default. What the chain buys them shows up the moment you measure. A goldfish, the fairground animal, the bowl on the dresser, hears from below 50 Hz up past 3,000, with thresholds so low that it became the standard laboratory animal of fish hearing for a century. the species against which everything else is calibrated. Some catfish reach higher still, toward 4 and 5,000 hertz. For comparison, a fish with no bladder is done below 300. The chain changes what kind of instrument the ear is. Why fresh water? Why did the great pressure-hearing dynasty conquer the rivers and never the reefs? Nobody is certain, and I would rather hand you the honest hypotheses than a tidy answer. Fresh water is often turbid with mud and tannin and algae, and where vision fails, hearing pays. Fresh water is shallow, and shallow water, as we saw, is acoustically cruel to the far field. Perhaps a supercharged pressure detector is what it takes to hear anything useful there at all. Rivers are also noisy in the low frequencies, current and turbulence roaring away down where bladderless hearing lives, so the lineage that could escape upward in frequency inherited a quiet, empty band, with no competition in it. Any of those stories may be true, all of them may be. The pattern is one of the sharpest in fish biology, and the explanation is still wide open. There's one more thing the electrode will tell you that the aquarium never does. Many autophysons don't just hear well, they vocalize. Croaks, drums, knocks, stridulations. And the same bladder that receives sound turns out to be a fine instrument for producing it. A resonating drum with dedicated muscles, in some groups that are among the fastest contracting muscles known in vertebrates. Hearing and voice, both hanging off the same repurposed lung. A private radio band, transmitter and receiver in one organ. So fresh water evolved its specialists by building a bone linkage. The sea evolved a different set, and the sea's version is, if anything, more extreme, because instead of sending the signal from the bladder to the skull, it sent the gas itself. Open the skull of a herring, and you find gas inside the bone itself. A pair of tiny gas-filled capsules, the size of peppercorns, sunk into the bone right beside the inner ears, each one split by a membrane with gas on one side and ear fluid on the other. They're called the prudic bullae, and they're fed by a duct of almost absurd delicacy, a gas line, thinner than a hair in places, running the length of the body from the swim bladder all the way forward into the head. The herring abolished the distance between the bubble and the ear. It laid pipe. Now the transduction happens at zero range. A pressure wave sweeps through, the gas in each capsule compresses and rebounds. The membrane between gas and fluid flexes with it, and that flexing pumps the ear fluid directly. The slosh delivered to the stones, with nothing lost in transit. Herring hear well, up into the thousands of hertz, and they hear quiet things, which is precisely what you'd predict from an antenna pressed against the receiver. The same plumbing does something no other fish does. Part of the flexing membrane's motion is routed outward, into the canals of the lateral line on the head. Give that a second, because it quietly breaks the boundary between two senses we spent an hour keeping separate. The lateral line, remember, is a near-field organ. Distant touch, one body length of reach, deaf to the far field by physics. In a herring, the bulla drives the lateral line with the pressure wave. The far field is piped into the touch organ. A herring in a school at night is feeling distant sound on its face, through an organ that in every other fish can only feel the water next door. Why would one fish need all this? Because a herring's entire strategy is the school, and the school at night is held together and warned by sound. These are animals that live and die by reaction time in darkness, in open water, with nothing to hide behind except each other and nothing to sense a predator with except pressure and motion. The bulla system buys milliseconds, and for a herring, milliseconds are the whole game. It also, almost certainly, lets them eavesdrop on each other in a stranger way. About 20 years ago, researchers recording captive herring at night kept picking up bursts of high-pitched pulses and traced them to the fish releasing streams of fine bubbles from the rear opening of the swim bladder duct. The bursts run for seconds at a time. They happen mostly in darkness, and they happen more when more fish are packed together, which looks like the statistical signature of a social signal. Whether it really is communication, and what it could possibly be saying, nobody has established. The honest label is real phenomenon, function unknown. But the picture of a herring school at night, thousands of the ocean's best pressure hearers, wired ear to lateral line, chattering in bubble bursts in the dark, should permanently retire the idea that a bait ball is a simple object. And then there's the herring cousin that heard the future coming. Remember the bill that came with the bladder. The bubble is a beacon. It shines at any sonar pointed at it, including the biological kind. The oceans of the last 30+ million years contain predators that hunt with clicks, at frequencies from tens of thousands to over 100,000 hertz. And to those predators, a herring school is a wall of lit mirrors. Every clupid in the sea swims around wearing a target. In 1997, David Mann, Jongmin Liu, and Arthur Popper published a result in the journal Nature that sounded, at first, like a measurement error. The American shad, a herring relative that runs up Atlantic rivers to spawn, responded cleanly and repeatably to ultrasound. To actual ultrasound, clicks, and tones reaching up toward 180,000 hertz, roughly 9 octaves above where a cod gives up, and squarely spanning the band of dolphin echolocation. Play shad an approaching train of sonar-like clicks, and they don't merely notice, they bolt. Organized directional flight away from the source, the signature of an animal that has evolved a dedicated alarm. Follow-up work drew the line through the family. The shads and their close kin respond to ultrasound. The true herrings and sardines apparently do not. The mechanism is still being argued about. The leading suspect is a specialization of the utricle, one of the 3 stone-bearing sacs, working together with that gas capsule plumbing, though exactly how it reaches 5 octaves above everything else in fish hearing hasn't been nailed down. What's nailed down is the function, and the function is the point. This is a radar detector. The bladder made these fish visible to biological sonar. Evolution's answer, in at least one branch of the family, was to learn to hear the searchlight itself. Power companies now exploit it. Ultrasonic projectors at water intakes turn shad away by the million, using the fish's own alarm against the architecture of a power plant. An arms race implies an opponent. We've now heard the opponent's weapon from the receiving end, a predator sweeping the dark with a beam of clicks pitched higher than anything else in the sea. Before we meet it face to face, there's unfinished business, because everything the bladder gave the fishes, range and bandwidth and sensitivity, it gave in a currency with no address on it. Pressure is a scalar. The bulla, the bone chain, the gas horn, all of them flood the ear with a signal that says everything about the sound except where it is. And that should worry you, because we left the fishes one coin flip away from swimming into a predator's mouth. Here's the paradox stated plainly. The motion channel, stones on hair cells, knows the axis of a sound and can't pick the end. The pressure channel, bladder and bulla and bone chain has range and bandwidth and carries no direction at all. It arrives at both ears of a small fish essentially identical, a number with the address torn off. Add the second channel to the first, and you haven't solved the coin flip. You've just made the coin louder. Worse than that, the bladder re-radiates its converted signal as motion, and that private broadcast washes over the very stones that were trying to read the true directional motion arriving from outside. On paper, the best hearing fish in the water should be the most lost. The way out is hiding in the physics of the wave itself, and it's the kind of solution that looks obvious for about 5 seconds after someone shows it to you, and unfindable before. A sound wave's 2 faces aren't independent. In a wave traveling through open water, pressure and particle motion are locked together in time, and the way they're locked depends on which direction the wave is going. Run the wave from your left. At the instant the squeeze peaks, the shove points one way. Run the same wave from your right, same axis, opposite direction, and at the instant the squeeze peaks, the shove points the other way. The axis is symmetric. The timing is not. The relationship between the two channels, whether they peak together or peak opposed, is different for the two ends of the line. So the tiebreaker is this: measure both. Read the axis from the motion channel, read the clock from the pressure channel. Compare the phase, whether the squeeze arrives with the shove or against it, and the ambiguity falls over. One bit of information was missing, and one bit is exactly what a second, different sensor can supply. The fish doesn't need the pressure channel to tell it where the sound is. It needs the pressure channel to tell it when the squeeze happens, so it can see which way the motion was pointing at that moment. The bubble is a timestamp. That's a lovely theory. The reason it's more than a theory is a series of experiments in the 1970s that deserve to be better known than they are. The central figure is a Dutch researcher named Arie Schuif, and his problem was the one that has haunted this whole field. You can't test directional hearing in a tank because a tank scrambles the very relationship between pressure and motion that the theory lives on. So the work went outdoors. Cages and calibrated sound projectors rigged in open water, in deep, quiet fjords and sea locks, with cod as the subject, trained with food rewards to report what they heard. Under those honest conditions, the cod did what decades of theory said no fish should be able to do. They told directions apart, left from right. And then the acid test, the one the coin flip forbids, front from behind, on the same axis. Given two sources at opposite ends of a line through the fish, the animals distinguished them reliably. Then came the manipulation that turns a demonstration into a mechanism. Working with Buwalda and with Hawkins across that decade, the experiments got surgical about the stimulus itself. Rigs that could control pressure and particle motion separately and flip the phase relationship between them. Flip the relationship so the squeeze arrives against the shove instead of with it, and you've built, physically, the signature of a sound coming from the opposite direction without moving the source an inch. The cod's judgments moved with the flip, the way the model demands. The fish were reading exactly the comparison the theory said they must be reading, the phase between the two channels. And there was one more result in that body of work, quieter and, I think, stranger. Cod could also discriminate distance. Two sources, same direction, different ranges, and the fish could tell them apart. Think about what could carry that information. Close to a source, in the near field, the ratio between pressure and motion changes with range. The two channels disagree by an amount that depends on how far away the source is. A two-channel ear, in principle, is a rangefinder. Whether that's truly how the cod did it hasn't been fully settled. But the discrimination itself was real, and it means the fish ear may be extracting not just a bearing, but something like a position. Be clear about what stands proven and what does not. That fish with pressure channels resolved the front-back ambiguity, demonstrated that the phase relationship is the cue, strongly supported by the flip experiments. How the brain does it, which circuits compare a sacule's shear against a bladder's timestamp, where the arithmetic lives, what the wiring diagram looks like, that, 50 years on, is still not mapped. Directional hearing in fish remains a field with a solved physics problem sitting on top of an unsolved biology problem, and the people in it'll tell you so. But step back from the open questions and look at the machine we've assembled across these rungs. Because it's worth seeing whole. A field of hair cells, each one an arrow, arrayed under stones in 3 tilted planes, reading the vector of particle motion down to sub-nanometer shear. A repurposed lung, converting the untouchable half of the wave into readable motion, extending range and bandwidth by orders of magnitude, and a comparison running somewhere in a brain the size of a pea that plays the two channels against each other in time to break the last symmetry physics left standing. No eardrum, no cochlea, no opening in the head. Every component borrowed from an organ that was originally for something else, balance or buoyancy or backbone, and the finished system localizes sound in 3 dimensions in a medium where our own ears can't manage a single degree. The fishes built all of that with gas they had to steal from the surface or squeeze out of their own blood, which raises a question about the animals that never had gas at all, the ones that solved buoyancy a different way, and in doing so, locked themselves out of the pressure channel forever. The ocean's oldest hunters. And the unsettling thing about sharks is what they turned out not to need. A shark has no swim bladder. No shark ever has. The lineage split from the bony fishes before the gas pouch was invented, and in 400 million years of otherwise relentless innovation, it never acquired one. The buoyancy problem got solved another way: the liver. A great white's liver can be a quarter of its body weight, swollen with oils lighter than water, a flotation tank made of chemistry instead of gas. And that choice, made deep in time for purposes with no connection to sound, set the acoustic terms of the shark's existence permanently. Oil doesn't compress. There's no bubble, no membrane, no cavity anywhere in the animal for a pressure wave to squeeze. Every consequence follows. A shark barely shows on an echo sounder, a ghost next to the blazing bladders of the bony fish. And a shark is utterly, structurally deaf to the pressure half of every sound in the sea, which makes the shark the great purist of this story. Its hearing is the inertia trick and nothing but. Stones on hair cells, particle motion, the low hundreds of hertz and downward. By every measure we've built up over the last hour, bandwidth, sensitivity to the traveling component, range on paper, the shark's ear is primitive. The temptation is to file it 2 rungs down the ladder and move on. Stay with the details for a moment first, because they're strange in ways the summary hides. A shark's ear stones aren't stones, for a start. Instead of the single sculpted otolith of a cod, there's a mass of small crystals bound in a paste, and in many sharks and rays that mass isn't even entirely homemade. The inner ear of an elasmobranch retains something almost every other vertebrate sealed shut: the endolymphatic ducts, thin channels running from the inner ear up to open pores on the top of the head. The ear is plumbed to the outside sea, and through those ducts, in some species, sand enters. Environmental grains, swallowed by the plumbing, incorporated into the sensory mass, pressing on the hair cells alongside the crystals. The body grew itself. You've heard this arrangement before. It's Cridal's shrimp, the animal that packs its gravity sensor with whatever dense grit the world provides, running in a predator the size of a boat, 500 million years after the trick was invented. If anyone ever repeats the iron filing experiment at shark scale, I would like to be told. Then there's the 4th patch. Alongside the 3 stone-bearing sacs, every fish carries a small extra bed of hair cells called the macula neglecta, the neglected patch, named for how little attention anyone paid it. In most fish, it's tiny. In big predatory sharks, it's enormous. In some species, it holds more hair cells than the stone organs do, and it has no stone at all. Its hair cells stand under a gelatinous cupula, lateral line style, and the patch sits directly beneath a soft spot in the skull roof called the parietal fossa, a thinning where the cartilage above the ear gives way to a window of skin. The arrangement reads like a directional instrument. Motion arriving from above and ahead passes through the window and works the patch. The anatomy was mapped and the pathway argued for decades ago, with the strongest evidence pointing at exactly the geometry a rising ambush predator would want: sensitivity to whatever is struggling at the surface overhead. Behavior, anatomy, and modeling all lean the same way. Call it well-supported rather than closed. Because that's the thing the summary really hides. Whatever the shark's ear lacks on paper, in the water it works, at range, And we know that from some of the most cinematic field experiments in marine biology. In the 1960s and 70s, Arthur Meerberg and his colleagues at the University of Miami lowered speakers into the open Atlantic and played sounds into empty blue water. No chum in the water, no bait, just sound. When the sound was low frequency, pulsed, and irregular, the acoustic signature of a fish in trouble, staggering rhythms below a few hundred hertz, sharks came. Silky sharks, oceanic whitetips, arriving out of open ocean within minutes from hundreds of yards away, converging on a loudspeaker. Steady tones didn't draw them. The pattern mattered. Irregularity, pulse, the arrhythmia of distress, and the mirror image result completed the picture. An abrupt, loud onset could make an approaching shark break off and withdraw. The folklore about splashing swimmers turns out to have a real acoustic core, and the animal behind it's a connoisseur of rhythm, tuned to one particular kind of failure in one particular band. Hold the two facts against each other. Motion-only hearing, the channel we said runs out a signal fast, attraction from hundreds of yards. The resolution is that the fall-off rules we learned in the near field don't forbid this. A loud, low-frequency source radiates particle motion into the far field, along with its pressure, thinning with distance, but never gone. And an animal with 4 patches of hair cells per ear, a giant neglected patch under a skull window, and 400 million years of tuning can work down near the floor of what physics leaves available. The shark moved into the limits of the motion channel, furnished the place, and became the best in the world at living there. And the motion channel has a basement, which is the last strange thing to say about it. Below 20 hertz, below anything you'd call a tone, the ocean is full of signal and fish hear it. Careful laboratory work, much of it from Olav Sand's group in Norway, the same lineage of researchers who pinned down the squid, has shown cod and perch responding to oscillations below 1 hertz, single slow shoves, closer to the tide's heartbeat than to sound. Juvenile salmon turn out to flee intense fields at around 10 hertz so reliably that Norwegian engineers have built the response into infrastructure, infrasound projectors at hydropower intakes, invisible fences made of nothing but slow-shoving water, steering millions of smolts away from turbine blades. A fence with no material in it, holding fish, because the fish's oldest sense treats a 10 hertz shove as an object it refuses to approach. Why would the basement band exist at all? One hypothesis, unproven and refusing to die, is that the infrasonic ocean is a map. Surf pounds coastlines, storms drum the surface, ocean waves interfering with each other ring the seafloor itself in perpetual micro-schisms, currents shoulder past headlands. All of it radiates infrasound through basins, patterned by geography. An animal that reads the pattern would carry a chart it never had to learn the shape of. Migrating salmon, returning eels, sharks crossing open ocean on straight lines towards seamounts. All of them do things that want an explanation. And the infrasonic chart is a candidate sitting quietly on the table. Nobody has caught an animal in the act of using it. I flag it because if it's ever confirmed, the sense we've been calling hearing will turn out to double as geography. Everything on the ladder so far, squid and herring and cod and shark, built its solution from water up, inside bodies that were always aquatic, out of organs that were already wet. The last builders came the other way. Their ancestors spent 300 million years perfecting the air ear, eardrum, and lever bones, and coiled cochlea, the whole terrestrial machine, and then walked back into the sea wearing it. Every problem we cataloged at the start, the ones that make a human being half-deaf in a swimming pool, they inherited in full. They couldn't start over. Evolution never starts over. What they did instead is the most complete act of biological re-engineering in the fossil record. 50 million years ago, the ancestors of whales were hoofed mammals standing in river shallows, and the fossils of the earliest ones Animals like Pakicetus, wolf-sized, long-skulled, found in what's now Pakistan, still carry ordinary land mammal ears. Eardrum facing the air, lever bones behind it. An ear built to catch thin vibrations out of the atmosphere and pump them into fluid. Then the lineage waded in and kept going. And every acoustic problem this story opened with landed on it at once. The eardrum, with water on both sides, became a pointless membrane. The skull, immersed, turned traitor. Sound stopped entering politely through two defined ports and soaked into the bone everywhere, smearing across both inner ears at once, erasing timing, erasing shadow, erasing direction. A whale ancestor in the water was exactly where you were in the swimming pool, hearing everything, locating nothing. Evolution couldn't throw the mammal ear away and start from a stone in a sack. It never gets to start over, it renovates. What it made of the Odontocetes, the toothed whales and the dolphins and porpoises and sperm whales, is the most sophisticated hearing system in the sea, and every piece of it's a repair. Repair 1. Cut the ear loose. In a dolphin, the bones housing the middle and inner ear aren't part of the skull. They form a separate capsule, the tympano-periodic complex, made of the densest bone known in any animal. So dense and so compact that whale ear bones survive when whole skeletons vanish. Fossil beds are littered with them, fist-sized and heavy as pebbles of iron, the most durable objects a whale's body makes. That capsule hangs outside the brain case, slung on ligaments in a cavity of its own. The traitor skull has been physically disconnected from the instrument. Repair 2. Bubble wrap. Around each hanging ear capsule, the dolphin maintains air spaces, sinuses filled with a stiff foam of air, mucus, and oil. Remember what an air gap does underwater. It's the one impedance cliff sound can't cross. The dolphin has wrapped each ear in exactly that cliff. Sound soaking through the head from the wrong directions hits foam and reflects away. Each ear listens out of its own acoustic window in its own shadow. And with isolation, the two ears disagree again. Timing differences, level differences. Everything your ears lost in the pool, rebuilt underwater with plumbing. Behavioral tests bear it out. A bottlenose dolphin can localize a click to about 1 degree, which is as good as you manage in air, done in a medium where sound moves 4.5 times faster and the geometry is 4.5 times less forgiving. Repair 3 is the strangest. And it answers a question you may have been holding since the start. If the eardrum is pointless and the ear canal of a dolphin is a vestigial thread, plugged and narrow and by every indication non-functional, then where does the sound get in? In 1964, the American cytologist Kenneth Norris proposed an answer that sounded like a provocation: through the jaw. The lower jawbone of a dolphin flares thin toward the rear, into a region called the pan bone, where the bone becomes a translucent pane. And behind that pane, running back toward the ear capsule, lies a body of fat unlike any other fat in the animal. Norris suggested sound entered through the thin bone, coupled into the fat, and rode it to the ear. It was received the way bold anatomical guesses usually are, politely and with reservations. And then every test that came afterward said he was right. Play sound through a transducer held against different parts of a trained dolphin's head, and the auditory responses peak around the pan bone and the fat channel behind it. Cover the lower jaw with a sound-damping hood, as experiments with trained animals did, and echolocation performance degrades. Cover the eyes, and nothing acoustic changes at all. The fats themselves deserve their own sentence, because they're not grease in the ordinary sense. Chemically, they're a class of lipids the dolphin manufactures for this location and almost nowhere else in its body, with a sound speed tuned close to that of seawater, a material selected molecule by molecule to be acoustically continuous with the ocean outside. The jaw fat is a waveguide, impedance matched at the front door, dense bone terminated at the back, A corridor of engineered tissue that does for the dolphin what the technician's gel does for the ultrasound probe, and the body treats it accordingly. In starving, emaciated, stranded dolphins, the blubber is burned away to nothing while the acoustic fat bodies remain. The animal will consume its insulation before it touches its instrument, so the dolphin's functional ear is its jaw and throat. Computer models of sound propagation through whole cetacean heads, work pioneered by Ted Cranford and colleagues who built entire skull and fat and tissue geometries into their simulations, found that in beaked whales, the best receiving channel runs in from below, through the throat region, between the jaws, up through the fat bodies to the ear capsules. A gular pathway. The animal hears through the underside of its head. For a predator hanging in black water listening downward for echoes rising off prey below, the receiving beam points exactly where the hunting happens. Hearing without ears was supposed to be a paradox. Hear its plain anatomy. The most acute hearing in the ocean belongs to a mammal whose external ears are sealed shut, listening through its jawbone. What that renovated instrument is for, of course, isn't just listening. An odontocete makes its own light. The clicks are generated up in the nasal passages, well away from the larynx, at a structure nicknamed the phonic lips, two ridges of tissue that snap together under air pressure, hundreds of times a second, each snap a broadband click. The clicks are focused on the way out by the melon, the rounded forehead, another body of acoustic fat, layered so that sound speed varies through it, bending the click energy into a beam the way a lens bends light. Out goes the beam, back come the echoes. In through the jaw and throat fats they arrive, to ears wrapped in foam compared across microseconds. The performance numbers on this system have been measured for decades in open water trials, and they stay astonishing no matter how many times you read them. A bottlenose dolphin detects a metal sphere the size of an orange at better than the length of a football field by echo alone. It discriminates between metal cylinders whose wall thicknesses differ by a few sheets of paper. It finds fish buried under inches of sand from the echo signature of a body that's mostly water. Because what its sonar lights up best, remember, is gas. And a buried fish still carries its bladder like a lamp it can't switch off. There's the arms race we set up hours ago, seen at last from the transmitting end. The dolphin's beams sweeping the dark, the bladders of the prey shining back. And in one lineage of herring cousins, an ultrasound alarm ringing at the first touch of the searchlight. The shad's radar detector and the dolphin's radar, locked together for 30 million years. Each one the reason the other exists, and the receiving hardware keeps up with demands no land ear ever faced. An echo from 6 feet closer arrives about 1,000th of a second sooner. A dolphin working a target adjusts its click timing on exactly that scale, waiting for each echo before sending the next pulse, tightening the interval as it closes. The auditory pathways of Odontocetes process click trains at rates, and with a temporal precision that sit at the extreme end of anything measured in mammals. An ear and brainstem running at sonar tempo. Hundreds of decisions a second in an animal that also somehow sleeps with half its brain at a time. One branch of the whales, then, went high, up into ultrasound, into beams and echoes and target discrimination, hearing rebuilt as an active instrument. The other branch of the family went the opposite direction. The baleen whales went low, and low in the ocean isn't a modest choice. Low is how you stop talking to a neighbor and start talking to a basin. A fin whale's call is a pulse at around 20 hertz, a note so low you'd feel it more than hear it, lasting about a second, repeated with metronomic patience, sometimes for hours. A blue whale works the same neighborhood, from the teens of hertz down toward 10. At the source, these are among the most powerful sustained sounds any living thing produces, in the same class as the radiated noise of a ship. And the wavelength of a 20 hertz call in seawater is over 200 feet, which means the largest animal in the history of life, an 80-foot blue whale, is small compared to its own voice. Every localization problem we gave the herring, the whale has at planetary scale. It lives inside single wavelengths of the sounds that matter to it. Keep that in mind for later, because how a baleen whale tells where another whale is calling from is still an open question, and the honest answer may involve baselines no laboratory could ever contain. First, though, an admission that this section is built differently from every other one in this film. For the squid, the cod, the shad, the dolphin, everything rested on trained animals and controlled trials, behavioral audiograms, thresholds, psychophysics. For the great baleen whales, there's none of that because there can't be. You don't put a fin whale in a tank and train it to press a paddle. No behavioral audiogram of a blue or fin whale exists. What we know about their hearing is inference, stacked from 3 directions: the frequencies they choose to produce, the anatomy of their inner ears, where the dimensions and stiffness gradients of the cochlea can be read, like the strings of an unplayable piano, to estimate what it was tuned for, and, most recently, simulation. The estimates converge on hearing centered far below ours, reaching down into infrasound. Convergent inference is, currently, all the evidence there is, and you should know that's the grade of steel this floor is made of. The simulation result, though, deserves its moment, because it lands the best inversion in this whole story. When Ted Cranford and the engineer Peter Kreisel built a fin whale's head, bone by bone and tissue by tissue, into a computer model and drove low-frequency sound at it, the best pathway to the ears ran through the skull. At those frequencies, the model says, the whole massive skull is set vibrating and conducts the sound to the ear complexes. Bone conduction, the very phenomenon that ruins directional hearing for every other player in this story, harnessed as the receiver. The skull, the organ that has been the traitor in every section so far, turns out, if the model is right, to be the antenna. It works as one precisely because it conducts everything. At 20 Hz, you don't want a small, isolated, discriminating ear. You want tonnage that trembles. Why go so low? Because of what the ocean does with low. Sound in the sea doesn't travel in straight lines. Its speed depends on temperature and pressure. Warm surface water is fast, the cold at depth is slow, and below that, mounting pressure makes it fast again. Somewhere in between, around 3,300 feet in the mid-latitudes, sits a minimum, a layer where sound moves slowest, and waves refract towards slow. Sound rising out of that layer bends back down. Sound diving below it bends back up. The minimum is a trap, a waveguide, a corridor of water that won't let sound escape upward to scatter at the surface, or downward to be swallowed by the seabed. Sound that enters near the axis of that channel spreads in something closer to 2 dimensions than 3, thinning far more slowly than open water spreading, and low frequencies, which the ocean barely absorbs, can ride it almost indefinitely. Oceanographers call it the SOFAR channel, and its discovery is a war story. In the 1940s, the American geophysicist Morris Ewing worked out from the physics that the deep sound channel had to exist, and proposed a use sharpened by wartime. A downed aviator could drop a small charge, timed to sink and detonate at channel depth, and listening stations thousands of miles away would hear it and triangulate the position from arrival times. It worked. Detonations of a few pounds of explosive were picked up across entire ocean basins. Decades later came the demonstration that retired the argument. In 1991, a research source lowered into the channel near Heard Island, in the far southern Indian Ocean, transmitted coded tones that were received near both coasts of the United States, paths approaching 10,000 miles, sound crossing most of a planet through water and arriving still legible. Now put the whale in the channel. In 1971, Roger Payne, fresh from revealing that humpback whales sing, published with Douglas Webb, a calculation that struck many colleagues as romantic arithmetic. Given the measured source levels of fin whale calls, their frequency, and the physics of the deep channel in the ocean as it existed before engine noise, whales should have been detectable to each other across distances measured in thousands of miles. Whale song at basin scale. The idea hung there, unresolvable, for 20 years, until the Cold War ended and the United States Navy began letting biologists listen through SOSUS, the classified network of hydrophone arrays built to track submarines across entire oceans. Christopher Clark of Cornell, among the first with access, described whales appearing on the arrays as the loudest things in the band. Blue whales tracked continuously as individuals. One followed for well over 1,000 miles of ocean, across more than a month, its voice never leaving the network's grasp. Singers off one coastline were being recorded on arrays moored off another. Detection at those ranges was no longer a calculation, it was a logbook. Detection, mind you, isn't conversation. An array with 1,000 miles of baseline hearing a whale doesn't prove another whale. With 2 ears, 11 feet apart, extracts anything at those ranges. Whether baleen whales actually communicate across basins, responding to each other, converging, coordinating, remains beyond what anyone has demonstrated. What the arrays proved is narrower and still enormous. The signal is there, crossing the basin, available. Payne's romantic arithmetic described a real channel carrying real voices. The open question is only how much of it the listeners use. And there are hints the calls may be doing something besides talking. 20 Hz sound doesn't just travel, it penetrates, reflecting off seamounts, continental slopes, islands, the basin's architecture. Some researchers who have tracked fin and blue whales moving through deep ocean suspect the animals may be using their own calls, or the ambient rumble of the sea, as a sounding line, long-wave echolocation off geography itself, a nautical chart read by ear. It's a hypothesis with nothing conclusive behind it yet, and no one has caught a whale ranging off a seamount and proven that's what it was doing. But an animal that migrates thousands of miles through black, featureless midwater on courses that stay improbably straight has some map we haven't identified. The infrasonic one is on the table, and it would mean the whale's voice doubles as its lantern. Hold the full picture of the baleen ocean for a moment, because we've arrived somewhere very strange. An animal whose skull is its antenna, whose calls are as loud as ships, living inside an acoustic channel that carries those calls across the width of an ocean. For a fin whale, the effective world, the sphere from which information arrives and into which its voice extends, isn't the water it can see, which in the deep is a few dozen feet, or the water it can swim through today. It's something closer to the basin itself. An animal whose sensory horizon is 1,000 miles lives in the Atlantic, all of it, the way you live in a room. Which is exactly why what happened next is the hinge between this story and us. Payne and Webb's calculation had a second half, and the second half was a subtraction. Their basin-spanning ranges were computed for the ocean before engines. Then they did the arithmetic again for the ocean they were sitting in. The ocean of 1971, already humming with propellers, and watched the whale's world shrink by an order of magnitude inside a single century. That subtraction has kept running ever since. We built our entire civilization's traffic inside the one channel the largest animals on Earth were using, in the one band they can hear. And for most of the time, we were doing it. Nobody was measuring what it cost. The noise of a ship is mostly bubbles. That detail is almost too neat given everything this story has been about. But it's the physics. A spinning propeller tears the water apart faster than pressure can hold it together, and the water boils cold into clouds of cavitation bubbles that collapse. Each collapse, a tiny concussion. Millions per second, merging into the broadband roar. That's the voice of global shipping. Gas bubbles gave the ocean its best ears. Gas bubbles, collapsing off 100,000 propellers, are what those ears are now full of. And the roar isn't spread evenly across the spectrum. It piles up at the bottom, below a few hundred hertz, in the exact band the baleen whales occupied for millions of years, riding the exact deep channel that carries sound furthest. We industrialize their frequencies, and the deep channel ducks our clatter the same way it ducks their calls. The trend has been measured at the same listening sites across decades. In the Northeast Pacific, low-frequency ambient noise rose by roughly 10 decibels between the 1960s and the early 2000s. 10 decibels is a tenfold increase in acoustic intensity. The background of the whale's world multiplied by 10 inside a single whale's lifetime, and a fin whale can live longer than the span of those measurements. Every threshold we've described, the nanometer shears, the phase comparisons, the arrays tuned near the floor of physics, now operates on top of that raised floor. What does a raised floor cost? Range, first. Hearing dies when signals drown, long before they vanish, and biologists quantify the loss as shrinking communication space, the volume of ocean from which one animal can still pick another out of the background. For North Atlantic right whales in the shipping corridors off New England, estimates put the loss at around 2/3. Whales that once heard each other across tens of miles now functionally alone beyond a few. The whales respond the way you do at a loud party. They call louder, the underwater version of the same reflex you use when you raise your voice without deciding to, and there's evidence right whale calls have shifted upward in pitch over the decades, edging out of the deepest, most contaminated band, a species renegotiating its own voice in real time around our traffic. Then, for one strange week, the traffic stopped, and the ocean ran the control experiment we could never have ethically designed. After September 11, 2001, Bakbesatiapanchion Aktintembrowant, shipping out of North American ports fell abruptly. In the Bay of Fundy, researchers happened to be doing two things at once that had never been combined: recording the underwater soundscape and collecting right whale droppings to assay stress hormones. When the ships paused, the low-frequency noise in the bay dropped by 6 decibels, and the whales' stress hormones dropped with it, measurably, in the samples, tracking the quiet. When shipping resumed, both rose again. It remains the most direct physiological evidence that ambient ship noise chronically stresses the animals on top of masking their communication, and that the fog we built has a biochemistry on the other side of it. Chronic fog is one kind of harm. There are sharper kinds. In March 2000, 17 whales, most of them beaked whales. The deep diving specialist with the throat channel hearing stranded along the Bahamas within hours of a naval exercise using powerful mid-frequency sonar, and this time the carcasses were fresh enough for pathology, hemorrhaging around the ears and brain. The United States Navy's own review acknowledged the sonar's role. The full mechanism is still argued over, with panic descents, tissue effects, and disrupted dive behavior all in play, but the pattern was established firmly enough that navies now plan exercises around it. Seismic survey air guns, used to sound for oil beneath the seabed, are louder still, fired for weeks on grids across whole exploration blocks. And one Australian study lowered the floor of what we thought was at stake. A single, small airgun, fired experimentally off Tasmania, was followed by a collapse in zooplankton abundance for more than half a mile around, with nets and sonar both showing the drop and dead krill larvae among the catch. One study, not yet replicated at scale, and it should be flagged exactly that way. But zooplankton are the bottom of the entire ocean food web, and if loud, impulsive sound harms them at that radius, the accounting for every airgun survey ever run is wrong. In the laboratory, meanwhile, scallop larvae raised under pile-driving-like playback develop malformed and delayed. Animals with no ears, no bladder, nothing but cilia and statocysts, damaged by the shaking of the water they grow in. Because that's the half of this the word noise hides. Almost everything we've measured about the harm is measured in pressure, and almost everything in the sea counted by individuals doesn't hear pressure. Run back down the ladder. Every squid and octopus, motion only. Every crab, shrimp, and lobster, on statists, motion. Every scallop, mussel, and worm, vibration and motion. Every shark and ray, motion. Every bladderless fish on every seabed, motion. The pressure hearers, the otophassans in their rivers, the herring, the whales, are the celebrities of this story, and they're a minority of the cast. For the majority, the injury that matters is delivered through the channel no regulation names. And sound in the sea has a third root we've barely mentioned, the ground itself. A pile driver doesn't only radiate into the water, it hammers the seabed, and vibration rolls out through the sediment as interface waves, hugging the bottom for great distances through the exact substrate where the clams, the worms, the flatfish, and the settling larvae live. The animals of the seafloor sit with their bodies against a struck drum, and the standard survey, a hydrophone hanging in the water column, doesn't even measure the drum. Larvae may be the highest stakes of all, because for larvae, sound is the address. Reef fish spawn into open water and their young drift for weeks in the blue. The reef they must find again is invisible from miles out and perfectly audible. The crackle of snapping shrimp, the grunts of fish, the whole rush-hour racket of a healthy reef propagates out into open water, and settlement stage larvae steer toward it, play reef recordings from empty moorings, and the larvae come to the loudspeakers. It works in reverse, too. On patches of dead coral, researchers broadcasting the sound of healthy reefs drew fish communities back in, and a degraded, silenced reef broadcasts its own emptiness outward, a lighthouse gone dark, unfindable by the very generation that would repopulate it. Now add a soundscape of engines over the top of all of it, and understand that the stakes of underwater noise aren't whales being annoyed. Their navigation infrastructure for entire ecosystems being jammed. So back to the mismatch, as promised, with teeth this time. Every impact assessment filed before the pile driver starts, every mitigation threshold in the permits, every received level criterion in the regulations of every major jurisdiction is written in decibels referenced to pressure, because the instrument of record is the hydrophone, and a hydrophone is a pressure sensor. The arithmetic that converts its readings into particle motion holds in the far field of deep open water, and, as we established at the very beginning, it fails near sources near the surface, near the seabed, and in shallow water generally, which is to say, precisely where the animals are, and precisely where the construction is. Measured comparisons in exactly those places have caught the real motion diverging from the pressure-derived estimate by an order of magnitude. The instruments to measure the real quantity exist. Particle motion sensors are accelerometers, the squid's organ rendered in electronics, and navies have deployed versions of them for decades. They're simply, overwhelmingly, not what gets lowered off the survey boat. Researchers, with Arthur Popper and Anthony Hawkins prominent among them, the same names that mapped fish hearing in the first place, have spent years documenting the gap in the scientific literature and pressing for particle motion standards, and the regulatory needle has barely moved. So the situation, stated as plainly as I can manage, the ocean's soundscape is audited in a currency most of its inhabitants can't perceive. Harm is delivered in a currency the audits don't count, and the shortfall between the two comes to most of the animals in the sea. None of that requires villains. Hydrophones are cheap, rugged, and standardized. Motion sensing is fiddly and young. Regulations inherit the instruments of the era that wrote them. The gap is a historical accident. But it's a gap you can now see with your own eyes because you know what the wave actually is. Two faces, one measured everywhere and one measured almost nowhere, and you know which face the staticists and the lateral lines and the seabed are turned toward. It took the whole climb to make that one sentence mean something, and it's the most consequential sentence here. Before the last stretch, one request, since you've stayed for all of it. In the comments, pick your instrument. Out of everything on this ladder, the stone in the bag, the flag in a breeze lateral line, the bone chain, the gas capsule pressed against the ear, the jaw of fat, the skull that trembles at 20 hertz. Tell me which one you'd carry if you had to live down there, and what you'd give up for it. And tell me which animal you think I shortchanged, because in 2 hours, I still had to leave whole phyla standing outside the door. If a documentary at this length and this depth is something you want more of, the like and the subscribe are the two signals that tell me to keep building them whole instead of cutting them into fragments. Now finish the climb properly by looking at both ends of it at once. At one end, the smallest working part in this entire story, a tip link, a filament a few billionths of a meter thick, strung between two rods on the top of a single hair cell, tugging open a single molecular gate. The deflection it needs is smaller than the width of the atoms it's built from. That event, one gate, one twitch, one ion current, is the fundamental transaction of hearing. And it's the same transaction in a jellyfish's statocyst, a herring's utricle, a shark's neglected patch, a whale's cochlea, and the ear you're using right now. Everything in this story, every escape and ambush and migration and song, cashes out at the bottom into that one movement. At the other end, the largest acoustic fact we know of. A pulse leaves a fin whale off one continental slope, drops into the deep channel, and crosses an ocean basin, thousands of miles of black water in a few hours, arriving still coherent, still carrying the shape it left with. One event again, one call, one channel, one crossing. Between the tip link and the basin crossing stand about 15 orders of magnitude of scale, and they're the two ends of a single system. The basin crossing wave is only information because somewhere at the far end, it'll tilt a stone, shear a bundle, stretch a link, open a gate. The largest signal in the living world terminates on the smallest switch in it. Hold both of those, and now try to answer the question the title asked, because it turns out we never actually answered it. How do ocean animals hear without ears? They don't. That was the wrong question, built on a wrong assumption. And the assumption was ours, that an ear is a thing, an organ, a landmark, a structure you can point to on the side of a head. Flaps and drums and canals. Anatomy. Strip the assumption and look at what we actually found, rung after rung. A stone in a bag of fluid, jelly on a flank, a crystal on a bed of arrows, a bubble against a membrane, a chain of vertebrae rocking against a lung, a pane of jawbone opening onto a corridor of fat, a skull that shakes. Not one of them is an ear by the anatomical definition, and every one of them is the same thing underneath. In every case, without exception, there are two pieces of matter that respond differently to the same wave: dense against light, stiff against soft, gas against flesh, held next to each other on purpose, with a nerve stretched across the disagreement. That's the definition. That's all it ever was. An ear is a discrepancy, a mismatch in matter, deliberately maintained, permanently wired. Whatever refuses to move with the body it lives in and gets red for its refusal is an ear. The head was packaging. The drum was one local solution among dozens. The only requirement, anywhere, at any scale, from the first blind speck of Precambrian life that noticed the water shove it sideways to the fin whale holding an ocean in its skull, is the mismatch and the wire. The sea is full of ears, and has been for 500 million years. Stones and bubbles and jellies and bones. Trillions of small disagreements, all of them being read, all of them keeping score, in the best sound-carrying medium on the planet. We swam through it with our air machines sealed against our skulls, heard almost nothing, and concluded it was silent. It was never silent. It was a room where everything is a microphone, where the water itself will carry a whisper across a basin and deliver it faithfully to anything built to disagree with itself, which is the coldest fact here, and the truest. Hearing is something matter does, wherever two densities meet and something keeps the score. Everything else, the lobe, the drum, the head, the word, is packaging.